This solution will be going over homework 29, which is 7.4, 6, and 12. An element in biaxial stress is subjected to the following stresses. Using Mohr's circle, determine the stresses acting on an element oriented at the following slope. So for both A and B, before we get started, I need to make a coordinate system for my Mohr circle. I will always start with my sigma axis, which is my horizontal axis, and some circle which has its center sitting on that sigma axis. The circle will always be centered somewhere on this sigma axis. Then, because I have to have 2 points that my circle is defined by, I am going to look at my stresses on the element that I have. I have a -29 and a 57 as my two stresses, and 0 for my tau. Since my tau is my vertical axis, and it's 0, I know that my 2 points must be on my sigma line, and since the only 2 points on my sigma line that are also coinciding with my circle are the endpoints, that's where I'm going to put my -29 and 57 megapascals. My tau axis has to go through sigma equals 0, so I can now draw that, and that will be roughly where it is. We don't need to measure it out exactly, but as long as we have a decent location for it, then our math will work out fine. So, we need, now that we have our circle, we need the stresses at some slope. So we're going to find our angle with our tangent, our rise over run, so 1 over 2.5. And because our Mohr circle is 2 theta, we're going to multiply our 22 degrees by 2 whenever we draw it. So we're going to actually be drawing our angle at the 44 degree mark, around there. And we want to find what is the coordinates of these two spots that we have a line for. My x, again, my x coordinate is my normal stress, and my y coordinate is my shear. So, I can say my shear will be my radius of my circle times sine 2 theta, because that gives me my vertical component. My sigma is going to be my radius times the cosine of that component plus or subtracted from the average location of my shear. So you can look at the center of my circle, that's my average stress, and then if you add or subtract r cosine 2 theta, you can see that that would be our horizontal component of these coordinates. My r and my average stress can be found with these equations. Our average is, of course, the sum divided by 2, and the radius is our magnitudes summed divided by 2. And this is just to get rid of the negatives if we have negatives. And we can plug all of that in, and we get our answer. So, if we now, for part B, it asks for the maximum shear stresses and the associated normal stresses, I'm going to use the exact same process, except now I'm drawing my line in a new spot. It's asking for my maximum shear stress, and if we look at our Mohr circle, we'll find the maximum shear if we have a vertical line going through the center of our circle, because that's going to give us our lowest and our highest position. And our angle from where we started from is 45 degrees. And this is just an easy cut and dry 45 simply because our original element is at the horizontal. Otherwise, you can't just look at that and see it. You would have to maybe do a little trig or something. But we're going to use the same equations. However, if you notice, our tau is just radius. We don't need to get the sine component of it because there is no horizontal component of this radius line. So it's just the radius. And then we can get rid of the radius completely for our y and x stresses, because again there's no horizontal element to the radius, and thus it will just be our average. So you can plug those in and we will get our correct answers. And then of course radius and sigma have the same equations as before. Or our average sigma, that is. So after plugging and chugging, noting that we're going to be rotating by some theta, and we can plot it with, this is the symbolic solution here, but if you want to plug the actual answers, this is what your two elements will look like. An element in plane stress is subjected to the following stresses. Using Mohr's circle, determine the stresses acting on an element oriented theta away from the x-axis. So I'm going to solve this symbolically, just so you can see that there's like a one and done easy way to do Mohr's circle every single time. So if I draw my sigma, I'm going to have my sigma axis, I'm going to have my circle on that axis, centered on it. My tau will be shifted off somehow by some amount. And it doesn't matter that I'm choosing that it's in the circle, I can have it out or in, whatever, it doesn't really matter. Symbolically it'll end up being the same, it's not going to change your answer. My two coordinates will be my x stress and my tau, and then my y stress and my negative tau, and those have to be touching the edge of the circle. And then we are going to be rotating it. Now in this problem it's not asking for any principal stresses, it's just saying we have some theta away. So since my theta is 40 degrees, this is going to be an 80 degree change, so 2 theta because it's more circle. I still need to know, and this is kind of where it's going to start becoming a mix of symbolic and exact solution, because we need to be measuring this with some 40 degree change about my x-axis. However, the solution that I'll make at the end will be symbolic at the end until we plug things in. So I'm rotating it by some angle, and my beta, which is also my 2 theta for what I would be getting from my arctangent equation, is going to be equal to my alpha plus my 2 theta from what originally is being moved. So pause, think about that until it makes sense. And then my alpha we can get by doing arctangent. And then this is from the textbook. However, if you wanted to just look at the circle, you know that tangent is a rise over a run. So you can rise an amount of, or rather you would lower by 2 tau, and then you run from y to x, and then since that would have been negative 2 tau over sigma y minus sigma x, it's also the same thing as this. You could also do it from the center to your endpoint, and you'll still get the same answer. Either way, we have our theta 1 is 18.6 degrees. That doesn't have too much application for our problem specifically. However, it is, well, this is one of the things we'll be plugging in when we're finding beta later when we're plugging stuff in. So, we recall these equations from earlier. However, our R is different. And the reason our R is different is because in the previous problem, we didn't have any shear stress. So all we had to do was say R was just the average of the magnitudes. But, and they also, yeah, we were able to derive that R based on the geometry of our shape. However, with a more symbolic, or a more general equation would be this one. So I can say, well, my radius is going to be, if I use Pythagorean's theorem, I can go from my center to my x position. So I have sigma x minus sigma average, square it plus my shear squared, root it all, and you get some hypotenuse value, which is my R. So I can plug all of this in. I can find sigma average. That it's just going to be the same equation as always, because that is always going to be just the horizontal elements. And then I have my beta that I just solved for, which is 2 of my theta 1, and my r. So I can plug everything in, and I get these answers. So, Mohr's circle. There's possibly a lot of questions. One could be, why do we use 2 theta instead of just theta? Or how does this work? Why are we able to just draw it on a circle? So I made a little animation that hopefully helps explain what's going on. And I'm going to keep it as simple as possible, and so hopefully it can be followed along and you can apply it to more complex scenarios. So if I have a cantilever beam and I only have an axial force, okay, as bare bone as possible, if I look at a stress element on this beam, it will have some sigma x, okay? So now if I want to graph this on my Mohr circle diagram, I have my sigma x where one of them is 0. This is my sigma y, it is 0. And my sigma x is going to be that force divided by the cross-sectional area, okay? Now my 0 is also my tau axis, so I'm just going to replace that and I can draw my circle. It's going to be this location. So my orange arrow will denote the magnitude of my y stress, and the purple will denote the magnitude of my x stress. Sorry, they're not the magnitudes of the stresses themselves, but if you include tau, because I'm going to be rotating this. But in other words, what I'm trying to say here is this: when you see orange on my blue square on the left side, that will be my y. And then the purple one, if you take the horizontal component of that from my Mohr circle, that represents the magnitude of my x stress. So, let's rotate this. All I did for my element is I rotated it by 90 degrees. And by so doing, my x component is now in my vertical and my y is in my horizontal. So it is the entire magnitude of my axial force is in what was my y direction. And in order for my components to reflect that on my Mohr circle, I had to rotate it an entire 180 degrees for my y to reach that location again. Meanwhile, I only had to rotate it 90 degrees for the actual element itself. So I'm going to do that again, but slower, and just watch both of them, and if it didn't make sense, hopefully it does this time. You can imagine at different locations of the Mohr circle where the magnitudes are changing and where the shear is also changing. I didn't put shear on here because that was way too complicated to animate, but that's what's happening here. Right here we have our maximum shear, and we have equal magnitudes for my sigma, x, and y. And when we have max shear, that means we rotated 45 degrees, but on a Mohr circle we have to rotate 90. So this is just a general rule of how it works. And then last, here's kind of an arbitrary location. Again, purple was the horizontal component of my purple arrow in my Mohrs is my x. So you can see it on my element here. It's not very much of it there. It's almost gone because that horizontal component, if you go down, it's very close to the 0. And for my y, the horizontal component is near the maximum principal stress that it could have had. I hope this was helpful, and if you struggle with Mohr's circle, that is okay. It took me a long time to really appreciate it like I do now. And then, of course, there are the other equations that you can always use. Anyways, have a great day.